Yeah. There you go. Yeah. Yeah.
Testing.
There's no one moderating before, right? I moderated it.
All right, good morning, everyone. Welcome to session 13 of this JWST conference. So I guess this will be the most explosive session, I think. So on supernovae and GRBs. So today, our first speaker is Tia Temimim. She's going to be giving an invited talk. Take it away.
Thank you so much. Can everyone hear me well? Great. I would like to thank the organizers for inviting me to give this talk. I was just amazed by all of the JWST results that I saw this week, and I am very excited to tell you today about what we are learning about supernova explosions with JWST. So this is a brief outline of what I will be talking about. I will first tell you about why studying supernova explosions is important, and then I will share some exciting results and some preliminary highlights from the JWST programs that I have been involved with in the last year. I will tell you about some very exciting results on understanding type 1A explosions, results on supernova 1987A, and then I will show you some spectacular data on galactic supernova remnants, Cas-A, and the Crab Nebula. And then I will end with a summary and future outlook. And what I want to stress is that the data and results that I am showing today is an effort of many individuals, and I will not be able to mention them all by name, but this is really a collective effort of these teams. So I want to start with some brief motivation. What I am showing here is a diagram of the evolutionary paths of the low mass sun-like stars on the left and the more massive stars that are about 8 or more times massive than the sun on the right. Throughout most of their lives, stars are fusing lighter elements into heavier ones in their cores. For sun-like stars, the cores are not going to get hot and dense enough to continue fusion past carbon, so those stars will end their lives in a non-explosive way. They will shed their outer layers and produce a planetary nebula, and what remains in the center is a hot core of a star made up of carbon and oxygen, and this is what we call a white dwarf. When white dwarfs interact with other stars in binary systems, they can produce explosions that we call type 1a supernova explosions, and these are explosions that are used as standard candles in cosmology. When we look to the right, we see the evolutionary paths of more massive stars. The evolution is very different. These stars will continue fusing elements all the way up to iron. When an iron core remains, the star will undergo a gravitational collapse and produce a supernova explosion. And these explosions are called core collapse supernova explosions. Supernova explosions are among the most energetic events in the universe. They have consequences for basically all areas of astrophysics. These are just some of the ways that they influence the galaxies in the universe. They greatly influence the energy balance and structure of galaxies. They enrich the galaxies with heavy elements and dust. They are important for feedback processes in the interstellar medium. They can trigger star formation. They produce black holes and neutron stars. They are also important. Understanding their progenitors can tell us important information about population synthesis, star formation histories, the initial mass function. It's important for understanding galaxy evolution. And finally, they're also important for cosmology, since they serve as standard candles, and they can be used to constrain cosmological parameters. So for all of these reasons, and there's too many to list here, supernovae are very consequential and important to understand, but there are still some important remaining questions. There are still some fundamental questions that we don't understand about supernovae. For example, what are the progenitors that produce the supernova explosions that we observe extragalactically, and the ones that produce the nearby supernova remnants that we observe, and how did these explosions occur? And this is what we're hoping to address with the JWST programs. I will start out by sharing some results on white dwarf supernova explosions with JWST. I am showing here this beautiful image, NGC 1566 from the FANG survey, and here is this type 1a supernova explosion in 2021 AEFX that was found in that galaxy. And the program aims to understand the origins of type 1a supernova explosions. These are thermonuclear explosions of white dwarfs. As I mentioned, they are used for cosmology, but we are still trying to understand if the origin of these explosions is when a white dwarf secretes matter from another star and then undergoes an explosion, or if it's a merger of two white dwarfs. So we are trying to understand these progenitor systems and their explosion mechanism. This program that I will talk about briefly is led by Saurabh Jha at Rutgers University, and it includes near-infrared and mid-infrared spectroscopy of 9 supernovae over 3 years. The first 3 have already been observed in the first year. And the reason James Webb is so crucial for observing these is because if we observe these supernovae in the infrared at later times, when the ejecta have expanded enough so that we can actually peer into the deepest layers, we can get a more complete picture of the ejecta abundances and the structure. And the infrared also contains lines that are not accessible at other wavelengths, and they are also less confused. So these are more isolated lines, and we can much better characterize their properties. So the first study that I will share is a study of a normal type 1a supernova that I showed in the image before, 2021 AEFX. This is a beautiful spectrum from NIRSpec and MIRI. You can see many of the emission lines. The optical is shown on the plot as well. And you'll notice here that when you look into the at optical wavelengths, the spectra are dominated by iron lines. But if you look towards the infrared, we see additional lines from cobalt and nickel, but also lines from intermediate mass elements like argon and calcium. And these lines have beautifully resolved structures that tell us about how the ejecta are distributed in these explosions. So what you're seeing on the right there are the zoomed-in regions on some of the lines. This is the work led by Lindsay Kwok, a graduate student at Rutgers. And what you'll notice there is that some of these intermediate mass element lines, like calcium and argon, have these flat top box-shaped structures. And we can tell from those structures that the ejecta extend to higher, the longer radii, higher velocities, they're broader, and the boxy profiles tell us that they are originating from a shell of material. But then when we look to the more massive elements like cobalt and nickel, they are more centrally peaked and they are Gaussians. And this tells us that the ejecta are stratified, that they have not experienced a lot of mixing, and this is consistent with the explosion originating from some type of a detonation. Also, there are the nickel lines are very strong, and it tells us that the density in the white dwarf where these were formed had to be very high, and that this is likely a white dwarf that was near the Chandrasekhar mass limit. In our program, we are also observing some of these more extreme white dwarf supernovae in order to understand their origins and also inform our understanding of the normal ones. This is an example of one of those. This is supernova 2022 PUL, and this is a more rare super Chandrasekhar mass supernova explosion. There are a couple of papers already posted on this object. One by Matt Siebert and another one by Lindsay Kwok, and there's another paper in preparation. And Matt has a poster on this object, so please see the poster for more details. But one of the most exciting things that we see that you might notice right away is we see this beautiful dust continuum. And that is extremely exciting because this is the first spectroscopic observation of a dust in a type 1a supernova explosion. We are still working on determining if this dust is pre-existing dust or if it is freshly formed. So please stay tuned for that. There are also other interesting things that come from the emission line strengths and asymmetries. You can talk to Matt for more details, but basically the lines are consistent with this supernova being produced by a merger of a violent merger of two white dwarfs, and that it happened within a circumstellar medium that is carbon and oxygen rich. Okay, so now I want to say a little bit about core collapse supernova explosions. These are supernova explosions that are produced by much more massive stars, 8 solar masses and above. The variety of core collapse supernova types that we observe are broadly divided in these type 1 and type 2 categories, and this is based on whether we see hydrogen and helium in the optical spectra of these supernovae. And what we understand now is that this is directly related to the mass loss that a star experiences prior to the supernova explosion. So for example, whether a star still has a hydrogen and helium envelope intact before explosion, or whether that envelope was removed prior to the explosion. And the standard view used to be that only the much more massive stars, like 25 solar masses and above, can shed these envelopes through stellar winds or eruptive mass loss, in which case these sort of stripped envelope explosions would be from the very massive stars. But now we understand that most stars are in binaries, and another way to strip that envelope is in a binary system. A binary can strip it from even a lower mass star. So we are currently trying to understand what types of progenitors, what types of systems produce these different supernova types that we observe. And that is the question that we're trying to understand. Okay, so not one way to understand that question is by looking at extragalactic supernovae, but another very powerful but complementary way is to study supernova remnants. Supernova remnants are remains of supernova explosions that we observed in the Milky Way and other nearby galaxies, and they can remain visible for thousands of years, but more importantly, they are resolved, and that's the key. When we look at supernova remnants, we can not only resolve the ejected material that was produced in the explosion, but also the surrounding circumstellar material, so we can use it to understand what type of mass loss the star experienced prior to explosion. This diagram here shows just the basic structure of a supernova remnant, what we are looking at when we take these observations. So we have the forward shock expanding into the circumstellar medium and heating that material. On the inside is the colder supernova ejecta that have not yet been reheated by a reverse shock that forms and then propagates back towards the center, reheating that material. And that material is reheated by the reverse shock to million-degree temperatures, and it emits in the X-rays. And this is an X-ray, beautiful X-ray image of the supernova remnant Casset. And I'm just going to zoom in on that just to show you the amount of detail and that we are able to see when we resolve these structures. What we are seeing here is signatures from the forward shock shown in blue. On the inside are these complicated filament and knot structures from the different elements that represent the reverse shock ejecta, and we even detect a compact object in the center. So these are the X-rays, the very hot gas, and now I'm going to show you what the JWST observations look like. Here we are. I believe most of you have probably already seen this image, but the infrared is just incredible. The amount of detail that we get with the sensitivity and spatial resolution of JWST is unlike anything that we've seen before for these remnants. It is giving us a view of emission components that we were not able to see before. And so just some things to point out, we are seeing emission from the interior ejecta that has not yet been reheated by the reverse shock. So it's something that we cannot see in the X-rays. And we see this beautiful emission from the circumstellar material that is highlighted here at the longer wavelength, so more in the orange color. And also the material that is reverse shock, which is mostly glowing in white, is resolved into these tiny clumps. So we are really getting to appreciate the type of ejecta distribution that occurs in these supernova explosions. And I am listing here just some of the science questions that we are able to probe with these observations. The list is not complete. There are many, but I want to highlight one specific aspect, and this is this region here. When we first saw this was the most unexpected aspect of this image. I mean, there are many, but that was very unique. And I'll zoom in on that. And here it is. So when we first saw this, we just were really surprised with these ring-like or bubble-like structure. And we, and probably everyone else that saw this image, and these are mostly the questions that we got, is what are those? What are those bubble-like structures? We've never seen anything like that in a supernova remnant. And we had some initial thoughts, two possibilities that came to mind. One is that this could be the interior supernova ejecta. That is because it's located, if I go back, it's in the center. It could be the interior ejecta, and in that case, what could these bubbles be? One thought that came to mind, well, these could be, for example, radioactive nickel clumps that created these bubbles in the interior. The other possibility is that this is actually circumstellar material, and that it's circumstellar material that the supernova shock is interacting with, and it might be in front or behind us, and we're just seeing it in projection. And this was actually quite a challenging task to try to figure out what these really are, because we not only needed to put together the IFU spectroscopy with NIRSPEC and MIRI, but we also needed to analyze the observations at other wavelengths and cross-correlate them with these structures. So these are just some preliminary results and thoughts about what this might be. When we look at IFU spectroscopy, the spectra are dominated by warm dust, and there are some lines that trace that ring structure, but they have very low velocities, almost close to zero, which makes us think that this is not rapidly expanding ejecta. Another aspect is that when we look in the X-rays, we are seeing that some of these structures correlate with gas that has CSM-like abundances. So now our thought is that this is actually circumstellar material that the supernova shock is interacting in. So then what then are these structures? Our current favorite theory is that these high velocity ejectonauts in Casset, which are observed, punctured through the CSM initially at very high velocities, and now the supernova shock is interacting with that material and highlighting the structure in that CSM, which is extremely cool. Okay, another thing I quickly want to show on Casset is one IFU position that we took right in the center of the remnant, And if you can see where it is, it's the white box that it's right in the middle. It's a region that's not really spectacular at first glance. It almost looks kind of empty. But what I want to highlight is when we look at this is the oxygen 4 line in that pencil beam through the remnant, it is extremely rich in emission and structure. We are seeing these loop-like structures. We are seeing small clumps. And this is important because this gives us a measurement of how clumpy and the ejecta are and what the filling factor is. And this type of measurement, it is extremely important for constraining models for supernova light curves and supernova explosion models. And this is really the only way to directly measure this, by looking at these systems. I want to say that there's a lot more coming for CAS-A. We also have near-cam observations that have their own surprises. So stay tuned for that coming in the hopefully next few months. Okay, now I want to switch to some observations of 87A. I'm showing here the near-cam image of 87A. That was a press release just a week ago, I think. And here is a comparison of the 87A image with Hubble. The JWST program is led by Mikako Matsura, and in the James Webb image, we see some interesting new structures that we haven't seen before. So I just want to overlay these labels that show the different structures. So we are seeing both in the HST and JWST image these outer knots that are outside of the main circumstellar ring that are now getting brighter as the shock is interacting with those outer regions. You see this diffuse emission that extends away from the ring that is in the JWST image, mostly dominated by synchrotron and traces the reverse shock. The very new thing are these crescent structures that are just outside of the main ejecta in the center. This is something that we haven't seen before, and what we think is that this is likely limb-brightened outer ejecta that is being heated by the X-rays produced with the shock interaction with the circumstellar ring. So yesterday, you saw these beautiful results in a talk by Josephine Larsen. These are results from the MIRI, MRS, and NIRSPEC observations of 87A. One of the most exciting results is that there is a signature from the central compact source that is seen in argon and sulfur emission. The possibilities for that emission are that it's a cooling neutron star or pulsar wind nebula. You also saw yesterday this beautiful NIRSPEC 3D emissivity map for the iron emission in the interior ejecta that really gives us a great view of the structure of those innermost regions and what the ejecta structure looks like. So I won't say too more about that since Josephine already covered this, but what I do want to show you are some additional results from the MIRI MRS observations. This is this beautiful spectrum of 87A for the entire system, covering NIRSPEC and MRS wavelength ranges. And the models that you see are models for different emission components that explain the spectrum, but what I want to draw your attention to is the dust continuum that you're seeing there. What we found is that it's interestingly best fitted by a two-component model of composite dust grains that are basically produced to match the ISM observations of dust. And the two different components that are shown there likely reflect the different grain sizes that are present in the circumstellar ring. So for example, the cooler grains are the larger grains, and the hotter grains in blue are the smaller grains. And I want to show you here how the evolution was changing of that infrared spectrum over time. The earlier observations in blue are the Spitzer observations that were taken at earlier times. And the bright magenta spectrum is the MRS spectrum that was taken recently. And what you'll notice right away is that that 20 micron silicate feature in the spectrum is increasing in strength, while the 10 micron feature is less bright. It's getting fainter. And if we look at the mass that is contained in these two components, we see that at these early times, with Spitzer, the mass was rising, and as the shock interacted with the circumstellar ring and was sweeping up more and more material, the dust mass was growing. But now with JWST, which are those points on the right side, the colder dust component has grown a little, but the hotter dust component dropped by a factor of about 2. And this means that we are seeing dust destruction in real time. So this is very exciting because dust destruction, understanding dust destruction, both in supernova ejecta and the ISM and circumstellar material, is extremely important for understanding dust evolution in galaxies in general. So we have a second epoch of MRS observations that we are currently analyzing, so we are very excited to continue monitoring this and to model the dust destruction. Now I want to tell you about a project that I am leading on the Crab Nebula. This is a program that aims to understand what type of supernova explosion created the Crab. I think most of you know about the Crab. It's a well-known object. It has served as a benchmark for understanding neutron stars and supernova explosions. There's now a consensus that the Crab resulted from a low mass progenitor, somewhere between 8 and 10 solar masses, and that it was a relatively low explosion energy. And for that reason, it was proposed to possibly be a supernova that resulted from an electron capture supernova. So the electron capture supernovae are different than the traditional or the typical iron core collapse supernovae that we think of. These supernovae occur from stars that are not quite massive enough to continue fusing elements all the way up to iron. They have oxygen, neon, and magnesium cores, and they are expected to have low explosion energies. And if the Crab was indeed an electron capture supernova, we would expect more neutron-rich material, and this is what we are hoping to measure with JWST, and what only JWST can measure. And I'll say why. This is not the JWST image. This is the Spitzer 24 micron image, and I just want to stress why we need JWST to measure this. Some of these important nickel lines that we want to measure, since we want to know the nickel to iron ratio, are emitting in the infrared, but the Crab filaments have such a complex ionization structure that in order to measure this accurately, we need not only the spatial resolution, but also spectral resolution to measure these lines accurately and determine the abundances. So I just want to give you a sneak peek into the data to see what kind of dramatic difference we are getting in resolution. I'll zoom in on a couple of regions here. Here it is with MIPS 24 microns. Here's the image with JWST. I'll highlight another one, this faint region on the top there, to tell you that's what it looks like, and this is what we have now. So the difference is just incredible. We are able to look at these regions get spectroscopy and measure some of these ratios in some of these filaments. Here's another region that's down here. This is where we have one of the IFU MRS spectra. That's the field of view, and I just want to show you here, this is the emission from one of the nickel-2 lines at 10.68 microns, just to show you what kind of structure we are resolving in the line to be able to measure this. Okay. Another thing that we are doing is producing a complete map of dust in the Crab Nebula to see where the grains are forming. And the reason we are able to do this is because we're leveraging the fact that 2 of the MIRI filters overlap in a region that allows us to subtract this sulfur-3 line. So this is a contribution from synchrotron dust, and the line there, the sulfur-3 line there in orange. And these are the contributions of those different emission components to the images. And by subtracting them with appropriate weightings, we can actually produce the first map of dust emission that tells us where the grains formed on small spatial scales. I'm just showing you a very quick snapshot of that. 21 microns, dust. So we are doing this for the entire remnant. I am not able to show the entire map yet. You might have noticed that, but those images are coming in the next month and a half or so, and I know I'm very biased, but I don't think you'll be disappointed by those. Please see a poster by my student Nicole Guntanis that shows the synchrotron study for the Crab Nebula, and she'll have a quick talk later today to tell you about that. There's another exciting, more exciting results on detecting dust in supernovae. I won't go into this because I'm almost out of time, but there are more talks in this session that will tell you about the dust reservoirs that we're finding in core collapse extragalactic supernovae that are showing us dust formation in real time, which is extremely exciting. And what I want to end with is sort of this blinking image between HST and JWST, just to show you how well they complement each other and just how much more information and detail we are getting from James Webb. It's just incredible. The HST images trace the reverse shocked ejecta, but with JWST, we are seeing the interior, we're seeing the circumstellar material is just unprecedented. And this is really the most detailed view of supernova evolution to date. These are just some of the things that we were able to do in year one, but I want to just say that this is just the tip of the iceberg. There are many more supernova remnants and supernovae that will provide important information. I'm showing here just some of my favorite ones, but there are many, and these all come from different progenitor systems. So if we are able to observe some of these other supernova explosions, this gives us a chance to connect the structure that we see in the remnants to the observations of extragalactic supernovae to really understand what types of progenitor systems produce these explosions. And of course, temporal monitoring over time, these are dynamic systems, they're always changing, allows us to study dust destruction and formation in real time, and of course, continued follow-up of nearby supernovae. I'll end there. Thank you very much. Oh, and just one quick thing to add. I also wanted to say that I really look forward to future years with JWST, and I want to echo what a lot of other people said, just to thank all the people that made this observatory possible. Thank you so much.
All right, so we have time for maybe 2 questions for Taylor. So we'll do one in person and then one online.
So I noticed the dust emission spectrum from CAS-A, I think I got that right, is silicates basically. It's all you see, the features, the 10 and 20 micron. Is that true for most supernovae? So is the dust mainly silicate dust from supernova?
So in CAS-A, you mean in this? Okay, the 87A. So 87A, the dust that you saw there was from the circumstellar material. It's not yet the ejecta dust. But the answer is no. There's a variety. We expect there are mostly silicons in the progenitors of more massive supernova, or in the more massive progenitors. But for the lower mass ones, for example, like the crab, we may expect more carbon dust. So it's actually I didn't mention this, but it's actually another interesting way to probe the mass of the progenitor star by studying what type of composition formed in the ejecta. So that is also something that we are doing.
Okay, we'll take a question online. Oh, yeah, sure. Yeah, sure.
Okay, we have a question from Biagire Simon, who asks, in the case of supernovae associated with GRBs that are often 1C broadlined, how can the James Webb improve our current knowledge about these particular classes? Is it the same improvement expected with supernovae 1B/C?
Oh, I think I'll probably defer that question to the GRB talk later, because I'm not. That's not my area of expertise. So I'll let the speaker later answer that. Thanks.
All right, listening to you again. All right, so our next speaker is Melissa Shabande.
Thanks, Ryan. Good morning, everyone. I have a question for you. What's the building block of the universe? Oh, that's true. Scientifically. Astronomically. What's the building block of the universe? Dust. Excellent. Cosmic dust. one of the most fascinating and important things we can do with JWST is studying the origins of cosmic dust, which is the focus of my talk today. My name is Melissa Shabande. I'm a postdoc here at the Space Telescope Institute, and I'm part of a wonderful team here called the Transient Science at Space Telescope. We study transients such as supernovae, novae, GRBs, and TDEs, and also dust formation. So why do we care about cosmic dust? So dust is behind star formation, interstellar reddening, planet formation, and if we can understand how dust absorbs and scatters light, then we can have a better understanding of the density, temperature, and heating and cooling rate of where dust is forming, and we can have a better understanding of the color of the background objects. And we can also constrain later stages of massive star evolution. So why do we care about supernovae? Because we have observed large amounts of dust in high redshift galaxies. Initially, it was believed that AGB stars are behind the significant amount of dust observed, but AGB stars were not old enough at the time to produce a significant amount of dust. So what is the alternative scenario? Supernovae, because they can efficiently and quickly spread material throughout the universe. So why are we using JWST? Because near-infrared and mid-infrared is transparent to dust. There has not been much of supernova and dust studies in the past, so it has not been studied well. The wavelength coverage and the sensitivity to cooler and warm dust that JWST provides we did not have before. And then we can also observe later epochs and fainter objects that we could not do with such telescopes in the past, such as the Spitzer. So what are the characteristics of dust that we can use to understand the origins of cosmic dust better? So one of them that we're after is to understand if dust is newly formed or it's been pre-existing. We also want to understand the heating mechanism of dust. We want to calculate the amount of dust and have a better understanding of how dust evolves over time. So on the right, I'm showing you this plot that shows the distribution of dust mass versus phase for supernovae that had some sort of dust mass measurement in the past. So all these dots are supernovae that had dust mass measurements by ground-based telescopes or Spitzer. And this one is 1987A. So we have this huge gap here. We're trying to study and observe more supernovae so we can add supernovae to this gap and constrain this dust trend better so we can understand how dust evolves over time. So this is one of our main goals, and we also want to understand the location, formation, heating mechanism, and the amount of dust in supernovae so we can ultimately understand the origin of cosmic dust. So here I'm showing you sort of a diagram of how dust evolves in supernovae. So here on the left is when a supernova explodes. So depending on the type of the supernova, we can start to see dust precursors showing up in the observation of supernovae at about 70 to 120 days. Dust precursors are these molecules such as carbon monoxide and silicon oxide that can cool the ejecta of a supernova to temperatures at which dust can form. We also want to observe supernovae at later phases from 100 days to about 300 days, so we can see how these dust precursors are evolving over time. And then we want to have observations past 300 days. This is when dust precursors have disappeared, and we expect to see dust signatures such as silicate and graphite showing up in the data of supernovae. So the first two stages from the explosion to up to 200 days is when we're observing supernovae to understand how dust forms, and then past 200 days is to calculate the amount of dust in supernovae. So I've divided this diagram into three different sort of logistical phases. Phase one is when we expect to see these dust precursors showing up in the observations. Phase two is when we're looking at the evolution of these dust precursors. And then phase three is when these dust precursors have disappeared and we're looking at the dust signatures. And we have several JWST programs at each phase. trying to study different types of supernovae at different phases. So we have a bunch of programs in phase 1, phase 2, and phase 3, which I'm going to talk about some of them in a bit. So first I'm going to focus on phase 1 and phase 2 of this diagram. So we have this DD program. We triggered observations on this nearby type 1c supernova. Type 1c are the ones that have lost their outer helium and hydrogen. So we tried to observe this supernova at around 50 days post discovery to see if we can see these molecules, the CO and SIO, if they show up in the observations or not. So this supernova is the first ever supernova spectrum with JWST. So top left shows the bluer filter of near spectrum of this type 1c supernova. The middle one is the red filter, and the bottom is MIRI, a lower resolution spectrum. So we have data from the optical all the way to 14 micron. We propose that we're going to see these molecules, CO and SIO, in the supernova early on at 50 days, which has not been done before, has not been seen before. But knowing that these molecules could form this early in these supernovae could indicate that these supernovae, if this is newly formed, these supernovae could be actually one of the main producers of dust in the early universe. So we saw the first overtone, the fundamental band of CO molecule, and we also saw silicon oxide in the MIRI spectrum. So on the right, I'm showing you these models that we're going to use. So this is a work in progress, but we're going to use these models to get a better understanding of how CO and SIO evolve over time, to get an understanding of their temperature change, their density change, and their velocity change. So we have another program. Again, in phase 1 and 2, we're looking at the dust precursors. So this time, we have a different type of supernova. This is a type 2p that still has the hydrogen and helium layers intact. So for this supernova 22 ACKO, this is relatively nearby. This is again a first ever type 2 supernova spectrum with JWST. So we got near spec and MIRI spectra similar to the type 1c, but this time this is around the same phase, about 50 days post explosion. We did not see the CO and SIO, and this could be because either we have these outer layers still intact and we cannot see the CO and SIO forming inside, or it has not formed. And this shows the significance of why we need to observe different types of supernovae. Supernovae have a huge diversity. You can see that 2 supernovae, both core collapse supernovae, and at around the same phase, one of them shows these dust precursors in the observations and one doesn't. So we tried to get a upper limit for the CO since we did not see the CO showing up in the spectra. So here in the bottom, you can see these 2 near spectra of the supernova. We use our models to get an upper limit for the CO so we can compare this CO mass with the upcoming observations at later epochs to see how much CO has formed over, let's say, 100 to 200 days post-explosion. We also could create the first spectral energy distribution of a core collapse supernova all the way from optical to 25 micron. And also we had these MIRI imaging that was observed by Fang's team that we added to our SCD, and it matches our spectra pretty well in terms of flux calibration. So now I'm going to focus on phase 3. This is when the dust precursors have disappeared, and we're trying to look at if dust has formed, if we see dust such as of silicate or graphite in the observations. So we have a program that looks at 5 type 2p supernovae. They still have their hydrogen intact. So the reason we picked these 5 type 2p supernovae for the sample is because these 5 supernovae have either shown dust signatures in the Spitzer data of them in the past, or they had some type of ground-based observations that shows dust precursors. So we observed 2 of them last year. I'm going to focus on these two today. So here you can see the image of 2004 ET, a supernova that exploded in 2004, a type 2P, another type 2P exploded in 2017 on the right. So the reason that these supernovae are still bright decades after explosion is because of the significant amount of dust that they host. You can see 04 ET is much brighter than 17 EAW because it's older, so it has accumulated more dust, and 17 EAW doesn't have as much dust because it's younger. So we use the photometry to model the dust that we see in both the supernovae. So using our models, we concluded that most probably the dust that we see in both supernovae here are newly formed. In 2017 AW, you can see this beautiful silicate emissions, which is telling us that most of the dust that we see in 17 EAW is made of silicate. For 04 ET, we concluded that the dust is most probably optically thick, meaning that we cannot see inside. So if we don't have a spectra, we cannot tell if it's silicate or carbon. And we also got a dust temperature, dust radius, and dust mass for both of them. The dust mass that we found for 04 ET is the highest dust mass ever measured in the mid-infrared, aside from 1987. So going back to this plot that I showed you earlier, so why do we need more than one supernova? Because supernovae have a huge diversity. They behave differently in terms of dust formation, and we have this huge gap here that we need to fill. So if I add these two supernovae that we observed with this program in cycle 1, 2017 EAW and 2004 ET, you can see that it starts to fill this gap. And we have 3 more supernovae from this program and other supernovae coming up that we're going to add here and constrain how dust evolves over time. Also, 2004 ET is the one that is hosts the second highest dust mass ever measured in the mid-infrared with JWST, aside from 87A. Taya just showed you this, and 87A was the supernova that had dust mass measurements at around 10,000 days, and that's the only one that we have. We're trying to fill out this gap, and 04 ET, the observations we had was at about 6,000 days. Almost done. So if I want you to take one thing away from my talk, is that supernovae are key to probe cosmic dust. JWST is the only facility that enables us to do this study. And we also need more data in terms of spectroscopy, photometry. We need a diversity of data, different types of supernovae, and we also need to observe the supernovae at different epochs, all the way from explosion to decades later. There's a talk coming up right after mine, presented by Zana. She's going to talk about a supernova 1980K that was found in one of our images. We also have a relevant poster presented by Ori Fox on a sample of dusty supernovae that we're trying to build over time. It includes one of the programs that I talked about today. There's another poster presented by Peter Hofleg. He's going to talk about supernovae observations spectroscopically with JWST. And I leave you with my summary. Thank you so much for listening.
All right, so we have time for just one question for Melissa. All right.
Okay.
Thank you. That was a very interesting talk. I was wondering, so this plot seems to just keep increasing with dust mass. Do you have a sense for what happens? Like, does it keep going up for, like, how long does it keep increasing the, like, dust production for these supernovae?
So we don't know that because we had 87A at 10,000 days. So if we have something older than that, or if we can observe 87A in the future, then we can have a better understanding of it. But we expect for dust to accumulate over time. So that's just gonna grow.
Thank you.
All right, let's thank Melissa again. All right, so our next speaker is Sana Zeros, as Melissa mentioned. So Sana, did you want to try to share your screen to present, or would you like us to do it?
Yes. Hi, everyone. Can you see my screen and can you hear me?
Yeah, we're setting up.
Can you hear me?
Right, yeah, you're good to go.
Okay, thank you so much. So hi, everybody. First of all, I would like to thank the organizers for this opportunity to present this work today. And also I would like to thank everyone who was working on this excellent space telescope. So my name is Sana Zsiros, and I just finished my PhD studies at the University of Szeged, Hungary. And today I'm going to present our paper on the serendipitous detection of the dusty type 2L 1980K with JWST's MIRI detector. So why dust is important for us? We already heard a lot about dust and supernovae, so I just try to highlight a few key points. So cosmic dust grains are the fundamental building blocks of our universe, and they contribute to several important astrophysical processes, for example, the formation of our solar system and our Earth. However, the sources are not clearly known yet, but the dust content of high redshift galaxies and also theoretical expectations suggest us that core collapse supernovae are one of the main stellar sources of dust. But the theoretical prediction and the observational estimates, as we can see on the plot about the dust growth in supernovae, are still not aligned. So there are still a lot of open questions regarding their contribution. In the past 2 decades, the Spitzer Space Telescope was the prime source of mid-infrared supernovae observations, but the JWST gives us a great new opportunity to see supernovae dust in details that never seen before, and also to fill in this supernova dust growth graph, hopefully. So what can happen to dust grains in the environment of core collapse supernovae? As you can see on this image, supernovae has a really complex environment. It is characterized by both the ejecta and the circumstellar matter. But basically, dust grains can be newly formed or pre-existing and heated. We can find newly formed dust in the supernova ejecta and also in the so-called cordons shell. On the other hand, pre-existing dust can be heated radiatively by the peak supernova luminosity or the CSM interaction, and dust grains can be heated collisionally by the collision of the supernova shock and the CSM. So we find the 80K in the 2666 Cycle 1 program, which aim was to investigate massive coal dust reservoirs which could be hidden at longer wavelengths. The original targets were 5 Type 2P supernovae, and as Melissa mentioned, 2004 AT and 17 EAW had already been observed and analyzed in in a paper led by Melissa, and really interesting results came out. So the second largest extragalactic mid-infrared dust mass was found in case of the 4AT. And if we take another look at the graph, we see that it starts to fill up, so really promising results. So here are all my contributors who worked on this paper, and as you can see, the 80K was a different type of supernova, and it is in the Fireworks galaxy, and it was captured by the MIRI detector on the images taken of the 4AT. And it was a really, really lucky detection, because as you can see, it was really on the edge of the image. Although it is more than 42 years old, the supernova was captured in all MIRI images, and it was identified as a point source. So just a few details on the supernova. It showed hydrogen alpha emission early on, which indicated ongoing CSM interaction, and also its late-time mid-infrared emission was explained by thermal and scattered light echoes. So here is the SCD from the MIRI observations. We also had additional data from Spitzer Space Telescope. They are in the bottom panel, this image, and we reanalyzed all available archived Spitzer data from the IRX and also the MIPS detectors. The images had large uncertainties, but we were able to constrain upper limits on shorter wavelengths, and also we were able to see whether the supernova shows a significant evolution over the course of the 15 years Spitzer images or not, and it didn't really show any significant evolution. So the first method was to model the thermal emission of the dust. And first we fit analytical models to the SCDs. We used blackbody and also analytical dust models assuming a spherically symmetric dust-containing region. We used amorphous carbon and silicate-dominated composition and also optically thin models. So the all 8-point SCD cannot be described with one component model, mainly because of the flux excess that we see at 5.6 microns. And also the supernova shows a close similarity to 1987A, which you can see with the gray line, its spectra. So some of the flux emission at some wavelengths can be explained by line emission. So here is our best fit model. And this best fit model resulted around 2 times 10 to the minus 3 silicate-dominated dust in case of the ATK, along with a hotter dust or gas component. The dust has quite a high temperature. It was around 150 kelvins. However, these models do not describe the location of the grains, so we cannot really conclude on the origin of the grains either. So to do so, and also to investigate in more parameters, we computed numerical models with the help of the moccasin radiative transfer code. So with moccasin, here are the best model with moccasin with purple. We found that the supernova can be described around 1.5 times 10 to the 17 centimeter big silicate-dominated dust shell. And as you can see on the plot, it is consistent with 1,000 Kelvin component, warm component also. So other than the modeling the thermal emission of the dust, we can also trace dust by modeling the optical line profile asymmetries. Because post-explosion supernova ejecta dust only absorbs light from the descending part of the ejecta, and this results that the red wing of the line profile is suppressed. And it's important to emphasize that pre-existing CSM dust, which is exterior to the ejecta, cannot resolve this. So we have a Keck optical spectrum, which was observed around the same time as the MIRI data. So it gives us a really great opportunity to model the optical line profile asymmetries, which we see in case of the hydrogen alpha and the oxygen doublet lines. So we modeled the optical line profile asymmetries with the help of Damocles, and we assumed a smooth and also clumpy dust density distribution. You can see our best models on the left-hand side in case of the hydrogen alpha and in case of the oxygen on the right-hand side. And we found that around 6-7 times 10 to the 17 centimeter thin silicate-dominated dust shell can describe ATK, which is really similar to the findings of the moccasin models. But interestingly, the optical line profiles resulted 2 orders of magnitude higher dust masses than the analytical models. So to get a full understanding on what's going on around ATK, we also investigated in the pre-existing dust scenario. So the MIRI images suggested that the dust has quite a high temperature, which means that there should be some extra heating source. And as I mentioned before, dust can be heated radiatively or collusionally. So the high degree similarity, what we see in case of the ATK comparing to the 1987A, it strengthens the collusionally heated pre-existing CSM scenario and also suggests that there should be a dust ring around the ATK and also something like a super ring with more dust than in case of the 87A. We also investigated in the relatively heated pre-existing CSM scenario with infrared echo models, and we found that it is a viable option that there is pre-existing CSM dust which can be heated radiatively in case of the ADK, and there is a continuous CSM interaction in the vicinity of ADK. So to conclude, we found from the mirror images that analytical and numerical SCD models reveal a surprisingly huge amount of silicate-dominated warm dust in the environment of ADK. And moreover, the optical line profiles disclose even larger dust masses. So we propose two possible explanations for this. First, we may see pre-existing CSM dust, which is heated collusionally, similarly like in case of the 1987A, or we may see mid-infrared component of the newly formed dust. And this is accompanied by a much colder dust, which is located in the ejecta. And just a few words on our program and just a quick update. So the other three supernova had been observed and really amazing images came out. So we are expecting really interesting results soon. And the main takeaway that with the help of JWST, many supernova may produce a significant amount of dust even at late time. And also to find out more about these interesting astrophysical laboratories, further data will be necessary. So thank you so much for your attention, and I'm happy to take questions.
All right, questions for Zana. So I have let's see, Ori's got a question.
Very nice talk, Sana. This is Ori Fox at Space Telescope. So what are the prospects of finding more old dusty supernovae in these archival images? Have you had any luck?
So it's really important, I think, to also dig in the archive images. Because as you see, it can give us some constraints on the dust mass of supernovae, and we hope to find more supernovae. And thank you for the question.
So I have a question. This is Ryan Lau. So we've seen, like, in the past couple talks that most of the SCDs seem to require like a warm and a cold dust SCD to fit it. Is that do you think that's ubiquitous amongst all supernova ejecta, or is it something that we're missing with the dust models?
Sorry, could you repeat the last sentence?
Yeah, is it something that's like we require a warm dust component and a cold dust component for pretty much all supernova dust that we're seeing, or is there just something that we're missing with, like, is there just one component, but maybe we don't have the dust opacities quite right to fit it?
I think both options can be viable. So it really depends on the nature of the supernova and also at the timeline. So are they young supernovae or are they older supernovae? Is there any CSM interaction or not? So I think it depends on the supernova. Thank you for the question.
Thanks. Any other questions for Zana? All right, if not, let's thank her again.
Thank you.
All right, so our next speaker is going to be Benjamin Schneider.
Okay. So can you hear me well? Okay. So hi everyone. So I'm Ben Schneider, a postdoc at MIT Kavli Institute. Thank you for having me, and thank you for giving me this opportunity to present this work. So I'm here as part of a much more larger collaboration to talk about the James Webb observation of the two brightest gamma ray bursts ever detected. So let's start by a quick introduction about gamma ray burst. So you can see here the Fermi gamma ray sky with the galaxy plane at the center, some bright gamma ray sources, and every day or every few days we detect a very bright source that overshine all other gamma ray source in the sky, and this brief flash of gamma ray burst is what we call a gamma ray burst. So they are among the most energetic phenomena of the universe, with a typical duration of few milliseconds to minutes, and we have discovered more than 10,000 of this event so far. So we traditionally divide the population into two main classes: short and hard gamma ray burst, and long and soft gamma ray burst, as you can see here. But very recently we observed a hybrid event with property consistent with a long JRB in terms of hardness and duration, but with a progenitor consistent with a short gamma ray burst. So we observed two main emissions from these events, a prompt and an afterglow emissions. The best model that we have to explain this emission currently is the fireball model. In this model, you have an ultra-relativistic jet. Inside the jet, you have internal shock produces this prompt emission, mainly composed of gamma ray emission. The jet can interact with the surrounding environment and through external shock produce this afterglow emission with from radio to X-rays. So even if these emissions are detected for the two main classes of JRB, their progenitor are thought to be very different. We think that short JRB are related to the coalescence of two compact objects, and that long JRB are related to the core collapse of fast rotating massive stars. Okay, so last October, a gamma ray burst was detected by all gamma ray satellites currently in operation. And this is here the comparison of the brightness of the gamma ray burst compared to the previous bright JRB detected. And you can see that is a very, very bright JRBs. And we refer it among the community as the brightest of all time, the boat. And when you look the previous distribution of brightness of a JRB, you can see that this JRB is clearly an outlier towards the 99 percentile of the distribution. And the rate to have such JRB is very, very low, below 1 per millennium. So this very bright, rare event pushes to have an extensive follow-up observation to better understand this JRB, including James Webb observation. So these bursts appear very near the galactic plane with a very high extension along the line of sight, as this has drastically complicated our analysis. Also, it is quite a local event compared to the typical median redshift distribution of long JRBs. Okay, so James Webb observed 3 times the field of this burst. The first time with with near spec and MIRI, and them at two different epochs with near spec and near cam. So the objective of these observations was to search possible signature of the supernova and also possible production of heavy elements. So you can see here the MIRI acquisition images with the burst at the center. We also had some HST observations, and you can see here a very recent James Webb observation of the field, and we can clearly see the bright host associated to this burst, and this burst is still clearly detected after almost 1 year. Okay, so this is the first mid-infrared spectrum of a JRB with James Webb. You can see here the spectrum with near spec and MIRI. So we have corrected the spectrum from the extension, and you can see we obtained this very typical polar law expected from the afterglow of a JRB. So there is no evidence of air process emission in this spectrum. There is also no clear evidence of supernova emissions, and this brings us to the conclusion that there is no evidence of a bright supernova associated to this JRB. Also, this observation, especially with MIRI, allows us to put a very hard constraint on the parameter of the afterglow at this epoch, given that MIRI is less affected by the dust extension that is quite high for this burst. Also, we cannot rule out that we have a possible fainter or bluer supernova with this observation. So the association with the supernova was largely debated among the community and depends strongly of the different assumptions that you are doing. And very recently, the group working on the near-spec, the late-time near-spec observation reports the detection of a very typical supernova associated to this burst. And you can see here their near-spec spectrum and the features obtained from consistent with the supernova observed. And this suggests that the supernova emission is decoupled from the central engine activity, and I think this also gives part of the answer that was asked earlier online. Okay, so then we also last March we have detected a long JRBs. Here you can see the light curve, and we rapidly identify as the second brightest JRB ever detected. You can see here the same plot that previously, and that this burst is also a bit out of the distribution. We also here you can see we also observe that the X-ray counterpart of this burst was very faint compared to the brightness of the burst, and you can see that is an outlier compared to what you expect from such burst. Also, we obtain a good localization after 1.5 days, and we start to externally follow up the JRB with ground-based telescope. But unfortunately, we were not able to obtain a redshift using the afterglow absorption lines, and this has also complicated the analysis. So we obtained a first epoch with the James Webb 1 month after the detection, the first detection, and here you can see one of the near-cam images. We obtained a near-spec images also, and here you can see the spectrum with a very red source. We also observe two emission lines that are consistent with an object at a redshift 4. And well, this raised a lot of questions. Is it a high Z scenario, a local scenario? In the case of high Z scenario, this raised some tension with the energy of the burst, and it could be also a very local event. So this observations were clearly inconclusive and pushed us to request a second observation with the James Webb. And the program was accepted, and we obtained 1 month later a new observation of the field. Here you can see the NIRCam filter for the first epoch, for the second epoch, and what we observed is the clear fading of the afterglow between the two epochs. And when you look at the fading of this source, it is very rapid fading, and we also observe this very rapid fading in the case of the kilonova associated to the gravitational merger in 2017. So we really favor the kilonova scenario for this burst. For the host galaxy, we suppose that the host galaxy is this bright face-on galaxy, very close, and that the progenitor were kicked out a long time ago by the galaxy before producing this burst. Okay, so going back to the spectrum, considering a kilonova scenario, the 2 points, the feature observed at 2.1 micron is consistent with the tellurium emission line produced from rapid neutrons capture, the Air process. It was also observed in the case of the kilonova associated with the gravitational merger. For the red emission, we interpreted as being due to the production of lanthanide elements. Okay, so these observations support the fact that GRB can produce heavy elements via rapid neutrons capture over a broad atomic mass range, and also that GRB play a key role in the heavy element nucleosynthesis across the universe. Okay, this is my conclusion. You have the link here of the two papers related to this analysis. So James Webb is also a game changer for study GRB. There are associated kilonova and there are supernova. Just I would like to highlight that over the past year, 5 deleted James Webb observation have been accepted to follow GRBs. And very recently, this summer, we observed another very interesting transient that are under analysis, but they are very promising. So yeah, thank you for your attention.
Questions for Ben?
Thank you for the talk. It was a spectacular result, especially with the kilonova. Do you have any insight into how a neutron star merger produces a long gamma ray burst as opposed to a short one?
Yeah, so there is some, I mean, it's still very recent, and people are working on that. But there is a paper claiming a precursor of this gamma ray burst, and they propose some possible progenitor for this burst. But yeah, I'm not sure there is a final answer to that right now. Already very good answer to that. So yeah, but I know that people are working on that.
Okay, I think we have a question online.
Yeah, so Biagio de Simone asks, is it possible for these two GRBs to rule out the presence of color evolution? If yes, which are the filters used to estimate the color indices and their variations?
So the color evolution of...
Is it possible for these two GRBs to rule out the presence of color evolution? If yes, which are the filters used to estimate the color indices and their variations? And then he adds to the Slack channel, GRBs 220 221009A and 230307A in late times with JWST. You can check the Slack channel for more details on the question if you'd like.
Yeah, I'm not sure what does it mean, the rule out the color even. Yeah, I'm not sure. Okay, I will check the.
Okay, I have a quick question. So, you mentioned an extinction correction for your mid-infrared spectra of the GRB. I'm wondering, like, what extinction curve you used to correct it, and how significant, I guess, or the uncertainties on that, and how they can affect your like power law that you're fitting to the continuum.
Yeah, so here this is the kind of so we are trying to reconcile the X-ray observation that should not too much affected from dust extension and this part of the spectrum. So we are fitting a model, and yeah, so the correction of the extension is we assume a model considering the galactic extension and also a galaxy, because you can also have some extension within the host galaxy. So we are considering from the galactic plan, I mean from the from our galaxy extension and for the host galaxy. So we are considering two different models, considering the best range in the mirror spectrum where we expect to be not too affected. And then we optimize this to correct the extension, and we find the value very close to the one that is expected, a bit higher, but yeah, a bit from value, yeah.
All right, thanks. All right, let's thank Ben again. All right, so now we have our poster presentations. So if our presenters could line up, and then I'm going to bring up those slides here. Okay, let's see.
Yeah, hi everyone, my name is Katja Farion. I'm a research fellow at ESA in the Netherlands, and with this poster I would like to show you some work that we did on NIRCam observations of Dorados. So Dorados is this star-forming region in the Large Magellanic Cloud, and it's in fact the most energetic star formation region in the local group. So JWST has observed this region, as have many other telescopes before, and I'm sure you all know this very beautiful public image that we have here. In addition to the public data, we're also using some very recently observed new NIRCam pointings that are a little bit further out from the central field. So what do we do with this data? The main goal is to study how stars form in this region. Where do they form? Do we see some spatial variations in where the young stars are, where the old stars are, especially with relation to also this massive cluster in there? So the first step was to look at the extinction. We looked at the extinction law from the red clump stars, which is shown in the bottom left corner here. Then we used this extinction law to create extinction corrected color magnitude diagrams, and then select different populations based on their ages, or as you see on the right hand corner in the top, also based on color combinations to select, for example, young embedded stars with infrared access or with access in emission lines. And then finally, in the bottom right corner, we study how are the spatial distributions looking like of these different populations, where the young stars, well, they're very centrally concentrated in at the position of this young star cluster, but there are also some diffuse young stars all over the field. While then if we look, for example, in the infrared axis, we can really peer into the very embedded phases, even out into the molecular filaments of this cloud. So if you're interested in that, please come talk to me, write me an email or on Slack. Thank you very much.
Hello, everyone. My name is Sam Rose, where I'm a graduate student at Caltech, where I work in the ZTF transient group advised by Monse Kazuo. I've been working on one object from a set of GTO Cycle 1 observations taken of 3 interesting infrared transients. Ryan Lau, Jacob Jensen, both here, also have objects from this program and also have posters, so I encourage you to check those out as well. The object I'm leading a paper on is AT2019-ABN. It was observed in January of 2019 by the ZTF. It's a member of a class of transients typically called gap transients, which are just peak between the luminosities of classical novae and supernovae. This class has sort of been separated in the last 15 years into a couple different classes, including intermediate luminosity red transients, of which 2019 ABN is thought to be a member. Also, luminous variables or supernova imposters, which are caused by the massive outbursts of massive stars, or luminous red novae, which are thought to result from stellar mergers. I bring those two classes up because while ILRTs have still not figured out what they are, but people sort of compare them to these other two classes of transients, since maybe they could be resulting from a similar process, but maybe for lower massive stars, as we see with the luminous red nova and the LBVs. One other really intriguing possibility for ILRTs is that they are actually electron capture supernova. So we've already heard a little bit about those today. It'd be really interesting if we could actually see what these look like even before they've exploded. Late time photometry of these events does fall below sort of progenitor luminosities. There are very red events coming from very red progenitors, but we haven't ruled out a colder dust component, so it's still not clear whether these are terminal or not. The JWST observations we obtained here are with near-spec and MIRI fixed-lit. The spectra are relatively featureless in the near-infrared with a very red continuum, but in the mid-infrared there are these very interesting paw features, which we don't quite know how to explain. There's a sort of broad feature at 8 microns and also a feature at 6.2 microns, which are typical of Class C paw features, which you usually see around like carbon-enriched post-AGB stars. It's kind of hard to interpret these. We thought in the context of a super AGB star explosion, because these are thought to be very oxygen-rich due to hot bottom burning. So I'd love to hear from the paw experts in the audience to sort of help interpret these results. I'll be at a poster session during the coffee break. Thank you.
Hello, my name's Nicole Guntanis. I'm a first-year graduate student at Ohio State. This work is my senior thesis at Princeton with Taya Tamim and Anatoly Spitskovsky. So the Crab Nebula serves as a laboratory for investigating high-energy particles and how they interact with their environments. For this project, I used JWST to investigate the infrared synchrotron-emitting particles in the Crab Nebula. So we took 2 synchrotron-dominated images of the Crab Nebula, one at 4.8 microns and one at 11.3 microns, and we calculated the spectral index, which is that equation up top, for each pixel between the 2 images, and this is the resulting spectral index map that we produced. And so you can see that the spectral index increases as you move outward from the center of the crab where the pulsar is, and that corresponds to synchrotron cooling persisting at these wavelengths. And this was found with Spitzer data previously. However, because of JWST's awesome resolution, we were able to make the index map in unprecedented detail. So here we have synchrotron emission at 4.8 microns, and you see complex structures like loops, sharp edges, and ribbon-like structures. And our index map, unlike Spitzer, is able to resolve these small structures. So we hope to use this high-resolution map to understand the origins of these substructures in the crab. And then finally, we calculated the mean surface brightness through several different regions in the crab, and we plotted it versus wavelengths for several different filters. And we found this unexpected bump at 5.6 microns. We hope that incoming MIRI calibration corrections will help us understand if this bump is not real or if it is real. And once we do that, we hope to fill out the crab broadband spectrum out to 25 microns. So if you have any questions about my poster, please feel free to contact me. And then finally, I'd like to give a shout out to all the co-PIs for this program. And thank you so much for giving me the opportunity to work on the crab with JWST. Thank you.
Online. I hope you can hear me.
Oh. Okay, all right, yeah.
Hello everyone, my name is Caroline Gieser. I'm a postdoc at the Max Planck Institute for Extraterrestrial Physics in Garching in Germany. And throughout this conference, I think it became very clear that massive stars are very important, from high redshift galaxies to the local universe. However, we still really haven't fully understood how they are even able to form, because their formation is fast, it's clustered, and in the early stages they are deeply embedded within their parental molecular cloud. With JWST we can now study the embedded phase of high-mass protostars, and the poster I am presenting on behalf of the European MIRI GTO project JOICE, that stands for JWST Observations of Young Protostars. The project targets both low and high mass protostars, and the first target that was observed was the high mass star forming region IRAS 23385 that is located in the Milky Way at a distance of about 5 kiloparsec. We have obtained a little mosaic with MIRI MRS and got full spectra from 5 to 28 micron, and the data revealed very interesting properties. We found deeply absorbed ice. We found deep ice absorption features, but also a plethora of atomic and molecular emission lines. For example, we use molecular hydrogen to create column density and temperature maps. And within these H2 lines, we detected multiple outflows going into all kinds of directions. And with James Webb, we can trace the warmer gas, but we also compared the properties of the cold gas that was derived from interferometric observations at millimeter wavelengths. So please check out the poster, and if you have any questions, then you can find me on Slack. Thank you.
Hi, my name is Laura Flagg, and the research I'm presenting here, it's a really fun project for me because it's an intersection of lots of things I love, like exoplanet atmospheres, debris disks, planet formation. There's no supernova, but we do have dust, so still somewhat relevant. So for systems with, we're studying exoplanet atmospheres for the first time at these longer wavelengths. And for the ERS target, WASP-39b, we have data from 0.6 to 12 microns. And from 0.6 to 10 microns, we pretty much have a good idea of what the spectrum is doing. And then at 10 microns, it takes an unexpected dip, as you can see in the middle column here. Please don't share this. So dips like these can be explained potentially by astrophysical contamination. If there is a background source emitting, it will dilute the transit and cause it. And if this source varies as a function of wavelength, this will show up in the transmission spectrum and cause a dip like this. And so, as someone with a background in planet formation, I see a feature at 10 microns, I think dust. So we looked at the stellar spectrum, and there does seem to be hints of potential infrared excess there, which is comparable to the level of infrared excess needed to cause the dip in the transmission spectrum. This infrared excess vaguely looks like that of either a black body or a crystalline silicate, with a caveat that there are significant systematic uncertainties in both that don't get plotted because they are systematic. The really cool thing, so yes, there could, the two take-home points is one, debris disks could cause contamination in your MIRI exoplanet data. Beware. And two, part I'm most excited about, if there is in fact a debris disk around a system like WST-39, a fairly big one, and this would be at a 4 or 5 AU. WST-39b has a superstellar metallicity and a substellar C/O ratio. And we exoplanet people really try to link these numbers back to planet formation, but it's really tricky because a low C/O ratio is highly degenerate. You can get it in a bunch of different ways. You can get it on, depending on formation location, you can get it with core mixing, and you can also get it. Yeah, planetesimal accretion causes low C/O. Sorry.
Okay, got the wrong ratio. Anyway, hello everyone. Good morning. I'm Jialu Li. I'm a postdoc from University of Maryland. I work with Edwin Bugert at Hawaii and Xander Tillens. So today I actually don't come with any JWST data, but I do bring some information that we learned from SOFIA Axis, which also works at, for example, mid-infrared 5 to 8 microns, but with very high spectral resolution of 50,000. We learned something from there, and we hope to deliver some information to the, for example, the community who would like to study molecular lines specifically to understand their abundance or column density, so on and so forth. So basically, the target I'm talking here is more in the scale of massive protostars, where we have a line with about just a few kilometers per second, which can barely be resolved by SOFIA Axis. So when we're studying this, we realize that with this high spectral resolution, we can really constrain the column density or partial coverage or line width very well. But however, this can be a problem if you have you have much lower spectral resolution. For example, at MRS, I know 3500 is good, but it's not good enough. This can be dangerous because we notice that when we compare our results with what ISO SWS got 20 years ago with a spectral resolution of 1,500, actually the derived column density can differ by 2 orders of magnitude. This is because when people are doing the fitting, they would like to, they prefer to pick up the most prominent and deepest strong lines first. And those lines are usually optically thick. And you might have the problem of the degeneracy in between line width or column density, so on and so forth. So one of the first piece of information I'd like to deliver is that please pay attention to optically thin lines because they will help you to constrain your column density within your beam. And then you can actually, there is a flow. If you do it step by step, you can decouple those parameters in a nice way. So this is what I call a standard recipe. And another one is a quick recipe. This is because even if MRS may not provide you that much good resolution, but it's possible to find pairs of isolated lines, specifically that share the same lower energy level. This is important because you would expect them to have the same column density, but because of their different Einstein A, they would have different line intensity. So ideally, if you can get rather, if you can really trust the data, the intensity, yeah. Okay, so you can use the line ratio to also give a reliable estimation of those parameters. Thank you.
Good morning, all. My name is Samuel Byler. I'm a 5th-year grad student at the University of Toledo, and I'm here to present something on the cooler end, looking at the first JWST SED of a Y dwarf. This is WISO 359, and if you look here in gray, you can see what previously we had for spectral coverage for this object, and now this beautiful spectral coverage that we have with JWST. We took near-spec clear prism data, MIRI LRS data, both fixed-lit, and we took 4 MIRI photometric points with the 10-micron photometric point being used to calibrate our MIRI LRS spectrum. And we get a bunch of beautiful features. We look here in the bottom left. We get our first detection of ammonia at 3 microns, which is our first clear detection of ammonia shortward of 5 microns in brown dwarfs. We also, at the 5-micron peak, where most of the flux is coming out, we find that we don't see any phosphine in our spectrum or in any of the 24 objects that we observed with our program. And this is something that is very unexpected. None of the models are able to produce this lack of phosphine, and so we have some interesting chemistry happening here. And then lastly, in the mid-infrared, we have this beautiful forest of ammonia lines. It's just beautiful spectrum. It's fun watching the older people in our field react to this spectra. It's just gorgeous. But the real reason we want this giant SED is so we can get better temperature estimates. And with a broadband SED and a precise parallax collected by Davy Kirkpatrick, we're able to drop our precision, our error on temperature by a factor of 5, getting a temperature of 467 Kelvin plus or minus 16 Kelvin. And this puts us at a very cold Y dwarf. And then one thing we find is that our temperature and our luminosity puts our object we are very discrepant with the low gravity from our best fit model in blue. That these best fit models want this to be a 20 million year object with about two Jupiter masses. Or if you look at our luminosity and assumed field age of 1 to 10 gigayears, we're getting something much closer to 9 to 30 Jupiter masses and a much older and much more reasonable age of that 1 to 10 gigayears. So that's all I have. Oh, 2 quick things for all the galaxy people. One, we have synthetic photometric data for all the James Webb photometric bands. So if you're worried about having brown dwarfs contaminating your sample, look there. And lastly, if you have MIRI LRS data, we have a workable wavelength calibration to fix the 0.05 micron inaccuracy in the MIRI LRS data. Please look in the paper for that. Thank you.
Hi everyone, I'm Ryota Yamaguchi, a grad student from Tokyo Institute of Technology and ISIS. So JWST MIRI provided us a unique opportunity to study the physical conditions of gaseous nebulae around very hot stars. We present an analysis of the observations of the Wolf-Rayet binary WR140 with the MIRI MRS under the early release science program JWST led by Mr. Lau. So here we focus on an analysis of the fine structure neon 5 lines at 14 and 24 micron to reveal the 3D structure of the colliding wind region. So we created a 3D line ratio map to the velocity axis shown in the center of the poster. So by considering critical density of these lines, the relation between the ratio and electron density is given as a function of temperature. The electron density for temperature of 10,000 Kelvin is shown at the left panels of the right figure. So right panels of the figure is the outcomes from the hydrodynamic simulations of colliding winds conducted by Mr. Russell. Please visit his poster for further description of this model. So as a result of our investigation, we found a remarkable alignment with the dense regions derived from the neon 5 line ratio and simulation results. This indicates a higher electron density in a wind colliding region for the first time. Thank you very much.
All right, let's thank all the speakers in this session again. All right, so yeah, we'll be wrapping up here, and then please be sure to come back at 11 a.m. sharp. Thank you.